Okay, Assalamualaikum and hi everyone. So in this video, we are going to continue our lesson chemistry in chapter 6, chemical equilibrium. So chapter 6 is consists of three parts, 6.1, 6.2 and 6.3. So in this video, we are going to discuss in 6.1 dynamic equilibrium and 6.2 equilibrium constant. Okay, so these are the learning outcomes for 6.1. So at the end of this lesson, you should be able to explain the reversible reaction, okay, tindak balas berbalik, then dynamic equilibrium and law of mass action, okay, hukum tindakan jisim. Alright, and then these are the learning outcomes number 2. Okay, we are going to state the characteristic of a system in equilibrium. Then we are going to interpret the curve of concentration reactants and products against times for a reversible reaction. So chemical reactions. So few chemical reactions proceed in only one direction. Okay, hanya beberapa sahaja tindak balas yang proceed di dalam satu arah. So A plus B produce C plus D. So this one is one direction. So these are the example of one direction reaction, which is we have methane CH4 react with chlorine in the presence of UV. So it will produce CH3Cl and HCl. Then most of chemical reactions are reversible at least to some extent. Okay. Alright, so A plus B and reverse to B produce A. So reversible reaction, tindak balas berbalik. So in reversible reaction, when A plus B, it will produce C plus D for the forward reaction. For the reverse reaction or backward, C plus D produce A plus B. So this one is the side of reactants, okay. Then this one is the side of products. So forward reaction that proceeds from left to right. Okay, forward ialah ke hadapan. So while backward is reaction that proceeds from right to left. Okay, daripada right to left is backward, and then from left to right is forward reaction. So reversible reactions which takes place in both forward and reverse reaction. Okay, tindak balas berbalik adalah tindak balas yang berlaku di antara forward dan juga reverse reaction. So these are the symbol. Okay, the symbol reversible indicates reversible reaction. So the concept of equilibrium. So let's say we have the reaction of SO2 plus O2 produce SO3. So the balance equation is we put 2 at SO2 and then 2 SO3. So as soon as some product molecules are formed, okay, semakin banyak produk terhasil, the reverse reaction process begin to take place and reactant are formed from product. Okay, so bila kita dapat produk, okay, bila kita dapat lebih banyak produk forward reaction, okay, reverse akan mula berlaku, dan reactant akan bertukar daripada akan terhasil daripada produk, meaning that it reverse. So after a certain time, okay, the net concentration of SO2, O2 and SO3 do not change. Okay, pada satu ketika, okay, tindak balas dia SO2, O2 dan juga SO3 dia tidak berubah. However, SO2 and O2 combining to form SO3 at the same time. Okay, pada masa yang sama dia akan menghasilkan SO3 and then decompose to form SO2 and O2. Okay, so dia punya concentration tidak berubah tetapi dia akan berlaku tindak balas. Alright. So sulfur dioxide and sulfur trioxide exist in equilibrium. So this is said that dia berlaku dalam keseimbangan. Okay. So next, dynamic equilibrium. In a reversible reaction, both forward and reverse reaction continue indefinitely even though equilibrium has been established. Okay. So dalam tindak balas berbalik, okay, kedua-dua tindak balas forward dan reverse, okay, ke hadapan dan ke belakang berlaku, okay, continue indefinitely even though equilibrium has been established. Therefore, chemical equilibrium is a dynamic process. Okay, tindak balas chemical equilibrium merupakan dynamic process. So the characteristic of dynamic equilibrium, reactant and product concentration are constant, meaning that it stop changing, and then the forward and reverse reaction rates become equal. Okay. So the graph of concentration of reactant and product against time. Okay, kita nak balas terhadap masa. So reactant produce B, A produce B, B produce A. So concentration of A akan decrease. Concentration of A will decrease with time. Okay, and then concentration of A decrease with time. Then concentration of A will increase with time, meningkat terhadap masa. After a certain time, concentration A and B remain unchanged. Okay, so pada masa ini T di sini, okay, concentration ini tidak berubah, tetapi reaction ini tidak berhenti. Okay, did not stop, dia cuma akan bergerak sahaja. Okay, tetapi tiada kenaikan dari segi concentration, reactant dan juga produk. So pada keadaan ini, sistem dikatakan said to be in a state of equilibrium. Alright, so these are the curve of reaction versus time. Okay, so A produce B, reactant produce product. So the forward reaction, and these are the reactant. Okay, they can reduce, okay, until it produce equilibrium. So rate of forward decrease as concentration A decrease with time, and then rate of reverse increase as the concentration B increase with time. So after a certain time, okay, both forward and reverse reaction are proceeding at equal rate. Okay, dia akan berlaku pada kadar yang sama, ke hadapan dan ke belakang, as concentration A and concentration B remains unchanged. Okay, concentration A dan B tidak berubah. So the system is in the state of equilibrium. Okay, sistem berada dalam keseimbangan. Okay, alright. So these are the example. N2O4 produce NO2. N2O4 is colorless. Okay, di sebelah kiri. Kalau di sebelah kiri dia colorless, kalau di sebelah kanan dia akan berwarna brown. So the frozen N2O4 sample is nearly colorless. Okay, maksudnya di sini dia dalam keadaan colorless. So on warming the N2O4, bila kita panaskan N2O4, it becomes a gas and partially dissociate to form a brown NO2. Okay, dan dia akan menjadi warna brown di sini. The colors stop changing when equilibrium is reached. Okay, warna akan berhenti, okay, berubah bila keseimbangan tercapai, meaning that the rate of forward and reverse reaction is equal. So these are the example. We use N2O4. Next, we proceed to law of mass action. Okay, hukum tindakan jisim. It is also known as equilibrium law. Okay, keseimbangan, hukum keseimbangan. So it is a relationship that relates, okay, hubungan yang menghubungkan concentration of reactant and products at equilibrium. Okay, consider this general reaction equation. So let's say we have equation A plus B produce C plus D. So where A, B and A, B, C, D, the capital A, B, C, D are the chemical species, okay, involved, and A, the small a, B, C and D are their coefficient in the balance equation. Perkali dia. Okay, this is the number. So according to the law of mass action, okay, mengikut hukum tindakan jisim, the equilibrium condition is described by this expression. K is equal to concentration C, power of C, concentration D, power of D, concentration of A, power of A, and concentration of B, power of B. So, yang dekat atas ni kita letakkan produk, yang di bawah ni kita letakkan reactant. So, the equilibrium constant expression is the ratio of a molar concentrations of the products, the molar concentration of the reactant, okay, with each concentration raised to a power equals to its coefficient in the balance chemical equation. So maksudnya di sini, okay, kuasa ni adalah kuasa dia punya apa? Coefficient perkali, okay, in the equation tadi. So the value of equilibrium constant expression K, it is a constant at any given temperature. Dia merupakan constant pada sebarang suhu, and it does not depend on the initial amount of reactants and products. Next, ciri-ciri, characteristics of a system in equilibrium. So we have closed system, okay, dia mesti berada di dalam closed system, rate of forward reaction equal to the rate of reverse reaction. Then the properties such as concentration, pressure, color of reactant and product are constant. Okay, ciri-ciri seperti concentration, tekanan dan warna adalah constant. And then the final equilibrium position is the same regardless of whether the equilibrium is approached from forward or reverse reaction. Okay, so kita ada 4 ciri-ciri sistem di dalam keseimbangan. So there are some activities. Okay, define reverse reaction, reversible reaction, and define law of mass action. Okay, state 2 characteristic of a system in equilibrium, dynamic equilibrium. Then draw a concentration against time to show the dynamic equilibrium. So these are your activity. Okay, so these are the answer. The definition for reversible reaction: it is a chemical reaction that can proceed in both and forward reverse reaction. Forward and reverse reaction. Satu markah. Then the definition for law of mass action. Law of mass action or equilibrium law is a relationship that relates the concentrations of reactants and products at equilibrium. Okay, number 2. 2 characteristic of system in dynamic equilibrium. So the rate of forward and reverse are equal. Then number 2, the concentration of reactant and products remain unchanged, meaning that it is constant. Okay, draw the concentration against time graph to show the dynamic equilibrium. So this is the graph, okay, to show the dynamic equilibrium, which is we must have the axis concentration versus time. And then the concentration of reactant will decrease, okay, dia akan turun, and the concentration of product will increase. Okay, after some time, okay, dia akan reach the dynamic equilibrium, which is the concentration of reactant and product remain constant. Okay, tiada kenaikan dan juga penurunan. Okay, so axis 1 mark, shape, okay, bentuk ni 1 markah, dan the label 1 mark. So altogether 3 marks for a graph. Okay, so that's for chapter 6.1. Okay, next 6.2, equilibrium constant. These are the learning outcomes for 6.2. Okay, at the end of the lesson, students should be able to, first one, we're going to define homogeneous and heterogeneous equilibria. Then we are going to write the expression for equilibrium constants in terms of Kc and partial pressure, Kp, okay, for the homogeneous and heterogeneous system. Then we are going to define the degree of dissociation, which is symbol we use alpha. And then we write the expression for reaction quotient Q. Okay, so dia sama je dengan K tapi kita gunakan Q. Okay, so kita akan tengok kenapa kita gunakan Q. Alright, homogeneous. Homogeneous mean the product and reactant are all in the same phase. Okay, kalau kita ada satu reaction, gas and gas. So these are the homogeneous equilibrium. These are the homogeneous equilibrium because all the phase is gas. For heterogeneous, product and reactant are in more than one phase, which is the different phase. This one is solid, solid, gas. And this one is solid, gas, and gas. Then this one is gas, liquid, and gas. So writing the expression Kc. So the subscript C, okay, C kecil ni, okay, is the concentration of the reacting species. Okay, bermaksud C itu adalah concentration. So product over reactant, okay. Concentration of product di atas, okay, reactant di bawah. Dan perkali, okay, kita kuasakan. And then N2O4 gas produce 2NO2 gas. So Kc is NO2 square over N2O4. So concentration of N2O4. Okay, sebab N2O4 tak ada perkali di sini, dia ada satu saja. Okay, jadi kita darab 1 kuasa 1 lah kat sini. Okay, and then NO2 ni, produk ni kita ada 2 sebab this one is 2 NO2. And this one, we have aqueous and aqueous. So the concentration is CH3CO minus, okay, times concentration of H plus over concentration of CH3COOH. So note that the unit of this concentration must be in molar or mole per liter. So when we write the expression, okay, untuk Kp pula, okay, so Kp bermaksud pressure. Jadi kalau untuk pressure, kita akan ambil semua gas saja. So Kp is equal to partial pressure of gas C times partial pressure of gas D, power of D. So this is the product. Okay, so this is the product. And this one part reactants. That's why bila kita nak tuliskan expression tu, okay, ke atas ni adalah product over reactant. Okay, alright. So the subscript P bermaksud partial pressure. Okay, untuk reacting gas species. Jadi maksudnya P ni untuk gas lah, selalunya untuk gas. Alright. So kalau untuk NO2, kita akan tulis Kp is equal to partial pressure NO2 square over partial pressure of N2O4. Sebab nitrogen gas ni dia ada pressure. Okay, this one is partial pressure of NH3 square over partial pressure of N2 times partial pressure of hydrogen cube. So note that the unit of pressure must be all in atm. Kalau Pascal, semua mesti dalam Pascal. Okay. So equilibrium constant expression Kc ataupun Kp also known as equilibrium law expression. So please keep in your mind that the equilibrium constant Kc and Kp is dimensionless, meaning that it has no unit of quantity. So Kp, okay, Kp is 4.07 exponential -2 at 500 Kelvin. And then this one is 1.67 at 500 Kelvin. So this one nilai Kc, this one is nilai Kp. So unit dia tiada, okay? Unit is dimensionless. So in quoting a value for the Kp and Kc, you must specify the balance equation, including the phase for each reactant and product and the temperature. So these are the example. Write the expression for Kc and Kp if applicable for the following reversible reaction at equilibrium. Note that you must balance the equation first. So kalau untuk A, dia sudah balance, okay, jadi tak ada, kita perlu balance dah. Okay, untuk this one kita ada Kc, okay, dan this one kita ada Kc dan juga Kp, okay, Kc and Kp. So this one kena balance. Okay, kita tengok O2. Okay, this one is O. So kalau kita letak 2 di sini, this one kita nak letak 2. Okay, so the balance equation. Okay. Untuk N2O5, okay, so we balance the equation, this one. So this one kita times 2. Okay, so bila kita times 2 di sini, okay, 2 times 2 is 4. 4 plus 2 is 6. So kalau kita letak di sini 2 times 2 4. Okay, 2 times 2 4. So this one 2 times 5 10. Jadi dekat sini kita kena letak 4. Okay, alright. Okay, so this one is 4. 4 times 2 8 plus 2 10. Okay, so these are the balance equation. Alright, so untuk Kc kita boleh tulis, Kp tak boleh tulis. Okay, untuk A ni kita tak boleh tulis Kp. Sebab apa kita tak tulis Kp? Okay, because di sini tiada gas. Okay, alright. Untuk yang di bawah ni, okay, the balance equation. Okay, kita ada Kc, kita ada Kp. Okay, so untuk partial pressure, NO2 square, okay, then partial pressure NO square, then partial pressure O2. So untuk KC, concentration of NO2 square over NO2 NO square times O2. Then for C, 2N2O5, okay, produce 4NO2 plus O2. So this one is for KC concentration, NO2 power of 4, and then oxygen power of 1, N2O5 power of 2. Then for KP, partial pressure of NO2, okay, power of 4, P oxygen over Pn2O5 square. Next, heterogeneous equilibrium. So for heterogeneous equilibrium, reactants and product are in different phase. Okay, so kalau different phase, di sini kita ada solid, this one is gas. Okay, only gas is taken into consideration, okay, untuk heterogeneous system. So at a given temperature, an equilibrium among CaCO3 and CaO and CO2 always lead to the same CO2 partial pressure as long as all three components are present. Okay, so this the large amount of CaCO3, small amount of CaO. Okay, then untuk figure B, okay, for figure B, small amount of CaCO3 and then large amount of CaO. So at the same temperature, pada suhu yang sama, the equilibrium pressure of CO2, okay, measure with a closed end manometer. Jadi kat sini kita ada manometer, okay, is the same in A ataupun B. Okay, it is independent on how much of solid CaCO3 and CaO present. Okay, so maksudnya dia tidak bergantung kepada solid di sini, because ini dalam keadaan fasa solid. So PCO2 does not depend on the amount of CaCO3 ataupun CaO. So experimentally, okay, the amount of CO2 does not depend on the concentration of CaCO3. Okay, why? This is because the concentration of a solid ataupun pure liquid is its density divided by its molar mass. Both density and the molar mass are constant. Okay, jadi bila dia constant, okay, concentration, okay, menjadi constant, thus the concentration of pure solid ataupun pure liquid has a constant value. Okay, dia mempunyai nilai yang malar. Okay, heterogeneous equilibrium. Okay, jadi bila kita nak write the expression, kita cuma ambil apa? CO2. Okay, jadi untuk CaCO3, this one is solid, this one also solid. Jadi kita letakkan dia sebagai constant tadi. Jadi K equilibrium CaO, okay, over CaCO3 times CO3. Jadi di sini adalah constant, jadi kita letakkan nilai 1. Jadi dia bersama dengan CO2 sahaja. Jadi Kc sama dengan concentration CO2, then this one is partial pressure CO2 only. Okay, so the concentration of pure solid, pure liquid and solvent do not appear in the equilibrium constant expression because it has a constant value. Okay, dia mempunyai nilai yang constant. Okay, so write the expression, okay, Kc and Kp if applicable for the following reversible reaction at equilibrium. So this one, kalau kita tengok di sini kita ada liquid, okay, jadi kita tak ambil kira untuk, kita boleh tulis untuk Kc saja. Jadi untuk Kc, okay, concentration H3O plus darab concentration F minus over concentration HF. Okay, kenapa kita tak ambil untuk water? Because water di sini phase dia adalah L, liquid. Okay, then NH4Cl solid. Okay, kalau yang ini kita akan ada, okay, untuk Kp yang ni tak ada. Okay, Kp tiada sebab semua ni di sini adalah aqueous saja. Okay, this one is aqueous. So untuk Kp, okay, kita boleh buat partial pressure HCl darab partial pressure NH3 over, okay, so jadi NH4Cl ini adalah solid, jadi tak adalah dekat bawah ni tak ada. Okay, Alright. Kalau untuk KC, okay, kalau untuk KC kita boleh tulis untuk ammonia dan H. Okay, untuk NH4Cl ini solid, jadi kita tak masuk dekat dalam expression. Jadi kalau untuk ini solid liquid, jadi kita tak masuk nilai ini. So this one, kalau untuk partial pressure, okay, partial pressure SO3 boleh wujud sebab dia gas. And then this one concentration pun boleh di sini. Okay, alright. 1 over PCO3. Sebab di sini dia adalah apa ni? Reactant. Okay. Next kita tengok relationship di antara Kp dan juga Kc. Dalam kebanyakan case, concentration Kc nilai dia tak sama dengan Kp. Okay, jadi bila kita nak write the expression, this one adalah untuk Kc, this one adalah untuk Kp. Jadi Kp is equal to Kc RT delta N. Ini ada kaitan dengan ideal gas equation. Jadi delta N is bilangan mole product minus bilangan mole of gases reactant, which is C plus D minus A plus B. Okay, so this is the dependence of equilibrium constant on chemical equation. Jadi kita tengok kat sini. Okay. Kalau equation kita A plus B produce C plus D, okay, constant kita letak K. When multiplying a factor N, NAA plus NBB produce NCC plus NDD, which is K power of N. Bila kita reverse the relation, C plus D produce A plus B. Jadi K tadi kita akan invert, jadi dia 1 over K. Bila kita reverse the N, kita multiply dengan nilai M, jadi C times M, D times M over M times A plus M times B. Okay, so this one is the constant. Okay, equilibrium constant 1 over K power of M. Okay. Alright, so kita tengok example di sini. The value of Kc and Kp depends on how the equilibrium equation is written and balanced. Jadi kita ada N2O4 gas produce 2NO2 gas. Jadi Kc NO2 square over N2O4 equal to 4.63 exponent negative 3. Jadi bila kita tuliskan equation ini, kita reverse dia akan jadi 2NO2 produce N2O4. Jadi Kc dia kita akan 1 over. Okay. Jadi bila kita 1 over, dia akan dapat 216. This one. Ini 1 over 4.63 exponent negative 3. So kita dapat 216. Okay, bila kita darabkan dengan half, okay, power of half, jadi concentration tu kita akan power of half di bawah. Okay, sebab ini di bahagian reactant. Jadi nilai dia pun lain, 0.068. Okay, next kita pergi the last part, iaitu degree of dissociation. Okay. Dissociation reaction, okay, a molecule is broken down into a smaller molecules, atoms ataupun ions. So these are the example. PCl5 gas produce PCl3G gas and Cl2 gas. N2O4 gas produce 2NO2 gas. NH4Cl solid, NH3 gas and HCl gas. The fraction or percentage of molecules that dissociates, okay, is known as the degree of dissociation. Value of alpha equal to 1 ataupun 100% sekiranya complete dissociation occurs. Kalau incomplete dissociation occurs, okay, penceraian tidak lengkap, alpha is equal to changes over initial. Okay, changes over initial times 100. Jadi the percentage equilibrium constant Kc and Kp do not change even if the percentage dissociation increase. Jadi nilai Kc dan Kp ni dia tak ada kaitan, dia tidak akan meningkatkan, okay, meningkat walaupun percentage dissociation increase. So what is reaction quotient? Q. Okay, it is a measure to figure out which direction reaction is likely to proceed. The value can be compared to the equilibrium constant to determine the direction of the reaction that is taking place. Okay, jadi Q ni kita akan gunakan pada awal. Okay, so it has the same form of equilibrium constant Kc dan juga Kp. Bentuk dia sama, cuma kita gunakan initial. The reaction quotient for general equation as given below, A plus B produce C plus D, which is not necessarily equilibrium quantities. Okay. By comparing the value of Q with K, it is possible to decide the direction of the system in order to achieve equilibrium. Okay, kalau Q is greater than K, nilai Q lebih besar daripada K, the ratio of initial concentration of products to reactant is too large. Okay, jadi kalau untuk mencapai keseimbangan, the product must be converted to reactant. Jadi kalau reactant di sebelah kiri, shift to the left. Okay, from right to left. Alright. Kalau Q sama dengan K, the initial concentration are equilibrium concentration, the system is already at equilibrium. Kalau Q is less than K, meaning that the ratio of initial concentration of product and reactants is too small. Jadi nilai dia terlalu kecil, jadi untuk mencapai keseimbangan, reactant perlu convert kepada produk. Jadi macam mana dia nak convert the product? Dia akan shift to the right, from left to right. Jadi maksudnya daripada reactant, dia akan produce more product. Okay, so that's all for chapter 6.1 and 6.2. Thank you, class.